So good afternoon and welcome to this tech talk entitled Medical Packaging and the Impact of Nitrogen Dioxide Sterilization. Today's talk is sponsored by Sterigenics, a leading global provider of outsourced terminal sterilization services for medical devices, pharmaceuticals, food safety, and advanced applicable markets. With their industry-recognized expertise, they help ensure the safety of millions of patients around the world every year. Across their 48 global facilities, they offer customers the complete range of sterilization services like gamma, ethylene oxide, X-ray, E-beam, and nitrogen dioxide sterilization. My name is Nicole Palick. I am the Senior Manager of the Expert Advisory Services team for both Nelson Labs and Sterigenics. So before we get started, I want to let you know the session is meant to be interactive. So questions are very welcome, especially to Jeremy over there. Oh, he's not there anymore. Oh, he's hiding in the back. You may ask questions at any time by raising your hands, and we also have a Q&A session set up for the end. So I'm going to introduce today's speaker. First of all, we have Alan, who will be coming up first. He's our Key Account Manager for Naxalizer Incorporated. Alan's distinguished 20-plus year career is showcased by a track record in building highly productive sales organizations and business units globally in medical, laboratory instruments, automation, IVD markets, and focus on capital equipment and chemicals. Prior to joining Naxalizer as a key account manager for nitrogen dioxide sterilization processes, Alan held senior sales and business development positions at Horriba Scientific, Thermo Scientific, Dynex Technologies, and Tican. Alan holds an advanced degree in business administration from the University of New Haven and 2 undergraduate degrees in chemistry engineering, and from the University of Connecticut. Our second presenter is going to be Jeremy Elwell, Senior Principal Engineer for Oliver Healthcare Packaging. Jeremy is a medical device packaging expert with more than 15 years of experience in the medical device industry. Prior to joining Oliver, Jeremy was a packaging engineer manager at Stryker, and before that, he held multiple roles in management and packaging engineering at Vention Medical. Jeremy is a proud Spartan, which hurts to say, but he is, having graduated from the School of Packaging at Michigan State University. So I'm going to go ahead and invite Alan up to the podium, and we will start our talk today.
Thank you, Nicole. How you all doing? Good. Okay, we're going to get started today. How do we advance it? I assume. I got it now. Little learning curve. Sorry, folks. All right, so the main objective here is to give everyone who's present an understanding of the work that we did, but more importantly, the benefits of NO2 sterilization and how it could pertain to your particular device and or product. In this presentation, we're going to go through the introduction of what NO2 is all about, as well as the process on how it works, as well as what products we are currently using NO2 for, which I hope will meet some of your needs, as well as results of the study on material packaging, which is key to today's talk. Just in summary, there are a lot of sterilization options one has to choose from for their products. These are listed as follows. We have traditional sterilization methods, which include dry heat, steam, autoclave. We have irradiation, which includes gamma, E-beam, X-ray, as well as gas, which I think everybody's familiar with, EO. More recently, due to the FDA, we've been encouraged to use alternative techniques, such as VHP, gas plasma sterilization, and what I'm going to talk to you about today, nitrogen dioxide sterilization. But when you consider the sterilant of choice, it's important that you understand and recognize as early as possible in your development cycles that all materials are not compatible with a single sterilant. We have to choose the best sterilant for the particular device and materials you're looking to sterilize. And that's really important to keep in mind as you develop your process and move forward in your clinical development cycles. So there are four main benefits of NO2. The first one is that it is a surface sterilization technique. Take into account a pre-filled syringe. It's not going to go inside the piston or inside affect the drug if it's capped. It's only going to hit those surfaces that can be wetted and where NO2 hits. And I'll talk about that later. The other benefit of NO2 is that it's a room temperature sterilant, in that we process typically at 10 degrees to 30 degrees C, basically ambient conditions. This is most important for if you're looking at a biologic, for instance, or a sensitive protein where you know it's going to be damaged by heat and or pressures. And last, the benefit is the minimal ingress in terms of residuals. We've done numerous studies, estimate in the hundreds, showing that residual values of NO2 post-sterilization is way below the TWA or the safety limit as imposed by NIOSH and or regulatory authorities. Two publications that are key to comparing NO2 with the other methods are those listed on the slides, which you'll be able to find after the conference when you look at our reference on the web. What I'd like to go through briefly is the kill mechanism, because I think that's important for you to understand how NO2 works. I guess it's not that bright. All right. On the left side of the slide, where you see that gray area, that gray region, that is your water layer or water boundary layer. And it could be monolithic, it could be multiple layers, it could be 20 layers in depth on your material or substrate. Or it could be on your skin, or not skin, but the product that you're looking to sterilize. All those equations that occur within that gray area are occurring in real time once NO2 is introduced to the humidity during the sterilization process. From that, I'll call it a soup of chemistry. It's really hard without a pointer. No, it's all right. I'll use a map. I'll go old school. I'll go old school.
There's actually a pointer right here.
All right.
And as long as you're off the screen, it'll be a cursor, but as soon as you go on, it turns into a laser pointer.
Okay, thank you. So we have all the reactions occurring during sterilization in the water layer at this point. Now, for your virus or bacteria that's looking to be sterilized, what happens is that you have a lensing effect whereby the NO and NO2 formed from this reactions that are going on gets picked up by the lipid layer of the bacteria or virus which you're looking to sterilize. And this reaction occurs to form N2O3. N2O3 reacts with the DNA and RNA associated with guanine and cysteine and basically destroys the virus. That's how it works. Here's the next slide is to show you a typical cycle for NO2. What we do after we install the load the sterilizer with product, we do some preconditioning where we basically evacuate the chamber several times to basically just temper the load, not temper the load, but condition the load in a preconditioning manner. We then draw the vacuum on it and introduce humidity where the cursor, where the pointer is right now. We introduce humidity to the load and then dose with NO2. At the peak of this curve is when we start administrating the dwell. So typically we're 1 times 10 to the minus, 1 times 10 to the 6 SEL in the fractional cycle at this point. We then repeat the vacuums and redo the introduction of humidity and NO2 to the process and repeat the dwell to make the full cycle. This aeration process post-dwell is done to evacuate and make sure that the load is effectively both sterile as well as fresh air ready. Key takeaways is that the dosing typically for an NO2 sterilization cycle ranges anywhere from 6 to, it says 15 megs per liter. That's on the high range. Typically we run around 10. Humidity ranges anywhere from 40% to 80% RH. Dwell time again is 10 minutes. Temperature, as I stated before, ranges from 18 degrees to 30 degrees C, on average 20 degrees C. And I think what's important that needs to be understood is that from the start of the load of the sterilizer to the end of aeration, you're looking at roughly a 4 to 8 hour process on average. Now, one thing I do want to bring into your attention is that the way our process works is that we do all of the aeration within the sterilizer. I repeat, all the aeration is done within the sterilizer. So this is a benefit to you that we'll summarize later on. The key one being is that when the load is removed from the sterilizer, it doesn't have to sit around for 1 or 2 days to aerate. There are 3 programs that we employ for NO2 sterilization. The first one is a near ambient program, and these are the process parameters that we typically use. Greater than 200 millibar, temperature range 10 to 30, 30 to 85% RH, 2 to 20 megs. The next one employs a vacuum cycle using ultrasonic humidification to administrate the humidity to the chamber. And the third one is we use steam humidification to introduce humidity to the chamber. Just to give you some attention, we are currently doing some of the work that we're currently involved with right now involve a lot of companies who are looking to bring NO2 into their processing. These are both clinical stage 2 as well as clinical stage 3 companies. We're working not only with pre-filled syringes, but also medical devices and implants. So you will not be the first person to use NO2. In fact, a lot of companies are ahead of you right now. The next question that typically is asked about NO2 is materials of compatibility. As I stated earlier in the conversation or presentation, no one sterilant is good for all materials. So for NO2, where we are strong is in the area of this column here, followed by for medical devices, these materials. The materials where we have some trouble with, and Jeremy's going to show you some of the results, deals with nylons and polyurethanes, as well as polyacetyl, which is your Delrin, and cellulosics, uncoated. Paper materials, if exposed to NO2, end up just basically falling apart if they're not coated beforehand going into the process. And again, cellulose acetate is another challenging material for the process. Another benefit of NO2 is that it's scalable. On the left is a laboratory R&D unit, which some of our customers are using for production. for small scale, small volume loads. They may need to run custom implants or some other device, a sensor or so. They would use the low 400 unit, which is the one on the left. The one on the right is more of our commercial line of products. This unit, in fact, is similar to the one that has been installed at Sterigenics at Petit Rachon for contract sterilization right now for commercial operation. This unit can handle up to a full pallet, which is equivalent to hold 16 totes of material, of standard US size totes on a US pallet. The important thing here is that we have the capability with this technology to scale this process. We have work on projects right now for a 5,000 liter as well as a 10,000 liter unit that's going to be used for sterilization and commercial use. So again, the benefits of NO2, it's need very little concentration for efficiency. So it's very efficient when you look at how much is needed for dosing to sterilize your product. The other point too is that the process parameters, the amount of humidity, the temperature, the pressure, the dwell, all of those are product specific. So we have a lot of flexibility in that we can maximize the sterilization process for both the physical properties as well as the sterilization requirements for your particular product. And we do that through feasibility studies and development. We've also have proven biocompatibility. We've run a number of PTOS studies on materials post NO2 sterilization and have no issues. It being a surface sterilant, it's going to not affect your drug product if you're looking at pre-filled syringes or deter to the chemistry that may be inside your packaging, since it only hits the exposed areas of the device during sterilization. Lastly is the short cycle times that I talked about earlier. The fact that from load to aerate to remove typically is 4 to 8 hours in length. And it really is easy to operate by an operator in the plant. So what I'd like to do at this point, having given you the taste of NO2 or the appetizer, I'd like to introduce my colleague Jeremy from Oliver to deliver the main course.
Thanks, Alan. That's a lot of pressure. Hi, everybody. How's everybody doing? I'm Jeremy from Oliver Healthcare Packaging. And yeah, I'm here to talk about the compatibility of NO2 sterilization with our packaging, some packaging that we put through a study that I'll go through. So whenever we get approached about a novel sterilization method, as Alan went through a couple, and one being NO2 sterilization, you know, we recommend following a process of like preliminary information to gather information about what you're looking at. Because there is a lot of, you know, talk right now about new sterilization modalities, and we get approached a lot of what works, what products work with it, why use it. And Alan went through a lot of good information about why to use NO2. But first, you know, identifying the modality, regulatory status, value proposition. You know, Alan went through a ton of good slides about that. Material compatibility is kind of where we come in, right? We have a lot to offer, a lot of packaging options to offer. But, you know, our process is just like yours may be too. We'll go to our standards out there, make sure that, you know, we're following all of our standards, ISO 11607, but also AAMI TIR 17. And for those of you that aren't familiar with that standard, it is a guidance document. And I think Alan might have gone through it a little bit, but compatible materials with different kinds of sterilization. And one of which is NO2. It has a full section, which I'll go through on the next slide. Also consulting with suppliers. So coming to Oliver, you know, asking us, going through the, you know, that conversation to talk about what kind of materials are compatible is a good place to start. Feasibility testing, looking at material properties, package integrity, and sterilization and aging. We actually have done a study with NO2, with Noxalizer. and I'll have results to show you, so we can show you some options that you may have if you want to pursue this sterilization type. So the AMI TIR document, which Alan and his team, they've helped author this section at NO2 sterilization. Table 17 here shown talks about thermoplastics. While most thermoplastics are going to be compatible, there are a little bit of concerns with a few, like nylon, like we talked about before, like Alan alluded to. I'll go into some of those pictures later on. But for the majority of thermoplastics, they're going to be mostly compatible with that sterilization type. So some of the design characteristics or the considerations: you want to process and packaging the primary sterile barrier system. Alan touched on it. You don't want to be in a carton, in a shipper. It's not compatible with paper-based, cellulose-based products. So you're doing it right in the sterile barrier packaging pouch tray system, directly in there, and then putting into your protective packaging afterwards. Also in there, it's not on here, but you do want breathable materials, but you want to stay away from medical paper. So the same reason as you want to stay away from cartons and shippers, you want to stay away from medical paper. So we highly recommend Tyvek for that. Seal strength, you want to look at seal strength in any application. You want to have it high enough to be above your minimum peel strength, low enough to be open, usable by the sterile at the end use in the sterile field. But seal strength, because there's not a lot of vacuum in this process, but because it goes through that, you want to make sure that you're really looking at a validated process when you look at the NO2 sterilization process. So here's our study where we started. We subjected samples to worst case NO2 sterilization. So you may ask yourself, well, what's worst case? In this case, we took 2 full sterilization cycles from Noxalizer, and over here in this table on your right, this has the parameters of that study, and this is one-time cycle. So we did 2 of those, and then subjected the packaging materials in this list to those 2 cycles. So the first one is uncoated Tyvek to a polyester-based film. The second is coated Tyvek to a PET-G tray. And third, we used a clean cut card. And for those of you, I hope you know what that is, because in this area, our facility in Anaheim is the old Clean Cut Industries. And it's now an Oliver facility. They make clean cut cards, which are backer cards made of HDPE that go inside of your sterile barrier system to help contain and hold your product, which there'll be pictures in the following slides. So the process that we followed is down here in the arrow. We prepared the samples. They didn't have product in it. These are empty pouches. We had the card inside one of the pouch. We had the tray material. It wasn't a tray. It was just a flat piece of PET-G. We subjected it to the 2 times Noxalizer sterilization, 2-year aging at 55C, and then testing within our Oliver lab. So this was not intended to be a validation, just a screening study, feasibility, just to get an idea of what that compatibility looks like for the materials that we put in the study. And these pictures down here show those samples being subjected to the cycle. So I'm going to go through a slew of test results. So it's going to be they're all going to be good. So, spoiler alert, everything's good. There's no surprises, but I did want to show some of the attributes we tested for so we can help screen for you before you go into a fuller, larger validation. So first is the uncoated Tyvek to 48 gauge polyester with a 2 mil low density polyethylene sealant layer. And these are pictures of non-sterile on the left and post NO2, the 2 times cycle on the right. So again, left and right, pre-sterile or non-sterile on the left, Noxalizer exposure on the right. We have tensile strength testing. We have elongation. The same test. You're just pulling the material. We did this test on the polyester side of the pouch for this one, and again, all good results. Tensile strength looked good. The elongation ended up to be good. Seal strength, we looked at a range. I don't know how well you can see it, but the green at the top, the red at the bottom is a min-max spread of seal strength. So on the left is pre-sterile, non-sterile, and on the right is Noxalizer exposure. So you can see the seal range is pretty similar. So that's one thing, probably the most critical thing we look at with our pouches and what packaging's kind of measured on in our field is seal strength, and that shows that it performed very well after that worst case sterilization 2-time cycle. And puncture resistance, that's also very important. 48 gauge polyester is a puncture resistant pouch, not as high as nylon, but it still has those properties for your packaging system. And again, inside out, outside in, we measured both, and everything looks very similar to pre-sterile overaging. This is 1 and 2 year aging study, if you can't see it on the bottom. Everything was looking good on that too. A little bit more of the same, but this one was our coated Tyvek, an Oliver coated Tyvek lid material to a 20 mil PET-G tray. Again, it's not the tray itself. It was just a coupon of PET-G material that we sealed to. So pre-sterile, post-sterile, everything looks pretty good with these. The test results, again, tensile elongation, looking good here. The seal strength, again, the range is there. It's a little bit higher of a seal strength starting gauge just because you have a higher seal strength when you're doing tray sealing. But the range actually got a little bit higher, but that could be variation in the test. That could be variation otherwise. These to us are very good results. And then the clean cut card. So if you weren't familiar before, this is the card. It's a flat card in this case, but it has and if you want to see a card, we have plenty of them at our booth over there. They're very interesting to see. Our designers do a ton of different card types with hold down features, 3-dimensional. They're very creative. It's really cool stuff. If you want to come see her at our booth afterwards. But we tested this through the Noxalizer process, and while we typically don't test tensile strength on these, we did it for this test, and puncture resistance doesn't really come into play since it's a really thick gauge of high density polyethylene. But tensile and puncture resistance both turned out really good. So those 3 combinations, they are very high runners for us. Polyester, Tyvek, PET-G with a coated Tyvek and clean cut cards are very common in the medical device industry. And those worked very well when we're looking at mechanical properties of Noxalizer. And so you may ask, well, what about stuff that doesn't work that well? And Alan already talked about this a little bit, and we knew going in, and for me, as an engineer, I like to go through, even if somebody tells me it's not any good, I want to know why. I just want to say, okay, well, show me why, so I know why, what I'm looking for in like a polyester, and say, okay, that one's good, and nylon didn't turn out so good. So in the bottom left-hand corner is a picture of pre-sterile and post-sterile nylon-based pouch with adhesive lamination, and that structure is shown here as well. So we did see in that study, we did that one. We didn't do testing for this because we knew it probably wasn't going to be compatible. So there was discoloration, a little bit of yellowing, a little bit of tackiness and wrinkling to the film itself. So when they put that in the guidance in AAMI TIR 17, that's the kind of guidance they're talking about. You want to stay away from your nylons in this process. But the good thing is, we have the other materials in the study. They didn't turn tacky, they didn't wrinkle, didn't discolor after sterilization. So we were happy with those. But again, as a reminder, you want to stay away from your medical paper. You want to stay away from craft paperboard. Paper labels and inserts all could react in negative ways during that cycle. So just to repeat it, if you do want to use NO2 sterilization, you're going to do it just like steam sterilization. You do it in the SBS pouch or tray or whatever else you guys can invent. So with that said, that's all I had for the study. Summary slide again. You want to go through it again, Alan, just for a reminder? We'll do that, and then we'll have a Q&A for you guys, and you can ask questions. Thanks.
So I hope we all had a good interaction in terms of understanding what NO2 is about. I think in summary, there are some strong points that you have to consider for your products and your processes. Again, the compatibility is good. Being an external surface sterilant, it's not going to interact with your drug product if you're doing drug product. Low temperatures you're working with, so your energy costs are going to be down. Again, the biocompatibility. But I think the fact that we brought the packaging into it we wanted to give everyone here a flavor for end to end on how NO2 would affect their product through the actual packaging of their products. So we'd like to, at this point, turn it over to questions and answers. Jeremy will come up. Does anybody have any questions? Ma'am. Okay. As I stated earlier, just to reiterate that the way these sterilizers are designed and the process is designed, they have internal scrubber systems built into the sterilizer to absorb the NO2 sterilant that's off gas from the load or that's not used or picked up by the load during sterilization. So it accumulates that in a scrubber material. It also has advanced sensors so that the door will not open so that the operator gets exposed to NO2 above what the TWA limit is, which is 1 ppm. Once it's removed from the sterilizer, we do recommend that the load, depending on the density of the load, sit at ambient for a couple hours before you shrink wrap or package it or put it into your transportation network. That's basically it.
Good question.
Any other questions? Yes, ma'am.
Oh, she's a teacher's pet.
Okay, good question. The question was regarding worst case and how do we develop a worst case scenario and why? The reason being is that the worst case per 14937 as well as 11138 involves the ability to stress the product and expose it more than you would in a typical cycle. Two reasons for this. One, you want to challenge your product's design to make sure that it can take a worst case scenario. Two is in the event of production, being able to recover your load in the event something goes wrong with the cycle. So whether or not you know, because these are expensive loads, whether or not you can continue and re-sterilize, that can only be assessed properly through doing the worst case studies. Yes, ma'am. I can't hear you. I'm sorry.
Compatible with nitinol.
What is nitinol? Is a inorganic, isn't it? Yes. So like stents? Yes.
How does the cost compare to EO and gamma?
It is more expensive. But it also is dependent on the load and density of the load. So every material has a different parameter sequence associated with effectiveness of the dose. So it's hard to say, you know, I can only just say from what we've seen, and I think Nicole can comment on it, is that EO is going to be cheaper. There's no question about it. Okay. Okay, any? Yes. Good question. Good question. The way that we develop these cycles, we have three basic steps that we employ. One is for people who are just curious whether or not NO2 will work with their product straightly from give it a sterilization, see what happens to the product. That's what we call an expose and return, or basically an expose and return. The next, as this lady asked, is that the feasibility studies where we go into more depth to assess what would be a lethal cycle typically for your product, coupled with we do a worst case as part of the feasibility study where we analyze the external and internal residuals, if any, depending on the product. In the case of implants where it's just external or a vial or a vial, it's just external residuals. We're not doing internal residuals, but we do the residual analysis as part, coupled with the worst case part of that study. And as far as timing is concerned, we typically for lethality have a 14-day grow out of the BI after we run our cycles, and we like to repeat that once we've identified a good lethal cycle. For the worst case application, typically that runs 30 days after worst case. So with availability of product, understanding that we can come to a lethality cycle relatively soon, we're looking at a 60-day process. I can't comment until we do the expose and return. Good question.
So I want to thank Alan and Jeremy for joining us today and their insights into nitrogen dioxide sterilization and packaging. And I want to thank you guys for coming as well and the great questions that you had. If you guys have any questions or you guys want some one-on-one time, Jeremy is at the Oliver booth in 1921, and Alan will be at the Sterigenics booth, which is 3135. So please come say hi to us. Thank you guys so much and have a great day.